Welcome, everyone. We're going to explore some really fundamental probability distributions. First up, problem 1, website conversion. Imagine a potential customer visits your e-commerce website. There's a 3% chance they will make a purchase. So part A asks, which distribution models whether this specific customer completes a purchase? Let's think about the clues here. We're looking at a single customer, and there are really only two outcomes, right? They either buy or they don't. That's right, it's the Bernoulli distribution. It's the simplest one, perfect for a single trial with a binary outcome. We can say x equals 1 for a purchase, which happens with a probability p of 0.03, and x equals 0 for no purchase with a probability of 1 minus p, which is 0.97. Simple as that. Okay, so for part B, what is the expected value or the mean for this situation? And what's the probability they don't make a purchase? Here's the great thing about Bernoulli. The formula is super easy. The expected value for a Bernoulli distribution is simply p. So in our case, the expected value E of x is 0.03. And the probability of no purchase? Well, that's just 1 minus p. So we do 1 minus 0.03, which gives us 0.97, or 97%. Fantastic. Let's move on to problem 2, customer service calls. A call center receives calls at an average rate of 15 calls per hour. The question for part A is, which distribution models the number of calls received in a 15-minute period? The key hints here are that we're counting random events over a fixed time period. Does a specific distribution come to mind? You got it, it's the Poisson distribution. It's perfect for this. Now, here's the first step, and it's an important one. We have to scale the rate, which we call lambda, for our 15-minute period. The original rate is 15 calls per hour, so we take 15 and multiply it by 15 minutes over 60 minutes per hour. That gives us a lambda of 3.75 calls per 15 minutes. As you can see on the slide, the probability of getting k calls is given by that classic Poisson formula. Now for part B. Given our rate, lambda is 3.75 per 15 minutes, what is the probability that exactly 3 calls are received in a 15-minute period? Okay, let's walk through this formula together. We need to calculate p of x equals 3 using our lambda of 3.75. So we plug the numbers into the formula you see on the screen. That's 3.75 to the power of 3 times e to the power of negative 3.75, all divided by 3 factorial. Let's break that down. 3.75 cubed is about 52.7. E to the negative 3.75 is about 0.0235. And 3 factorial is just 3, 6. When you crunch all those numbers, you get approximately 0.2066. So there's about a 21% chance of getting exactly 3 calls. Not bad. Problem 3. The die roll. A classic. A standard 6-sided die is rolled once. Part A asks, which distribution models the number that appears on top? Think about it. Are all the outcomes equally likely? The name starts with a U. Of course, it's the discrete uniform distribution. This one's straightforward. Each of the 6 outcomes, 1, 2, 3, 4, 5, or 6, has an equal probability. So, p of x equals k is simply 1 divided by 6 for any of those numbers. Okay, part B. If the probability for any single number is 1/6, what is the probability of rolling a 2, a 3, or a 4? Well, since these events are mutually exclusive, you can't roll a 2 and a 3 at the same time. We can just add their probabilities together. So we take the probability of rolling a 2, which is 1/6, plus the probability of a 3, another 1/6, plus the probability of a 4, which is, you guessed it, 1/6. That gives us 3 divided by 6, which simplifies to 1/2, or 50%. Easy peasy. Now for a more complex one. Problem 4, income distribution. Household income data is often right-skewed. This means most people earn lower to middle incomes, and there's a long tail of very high earners. So part A is which distribution often models this kind of data. Here's a hint. When you take the log of something that's right-skewed, it often becomes normal. This is the log-normal distribution. It's perfect for modeling positive values that tend to grow multiplicatively, like income or stock prices. The key idea is this. If the income, x, is log-normally distributed, then the natural log of x follows a normal distribution. You can see the notation there. ln of x is distributed normally with mean mu and variance sigma squared. Okay, this next part has a few steps, so let's walk through it carefully together. For part B, let's assume the natural log of income is normally distributed with a mean, we'll call it mu sublog, of 11.2, and a standard deviation, sigma sublog, of 0.7. The question is, what percentage of households earn more than $150,000? Okay, we are going to walk through this entire process together, step by step. Step 1. We can't work with the dollar amount directly. We have to transform the income threshold to the log scale. So we take the natural log of 150,000, which is approximately 11.918. Step 2. Now we calculate the z-score. Remember that formula? It's our value minus the mean divided by the standard deviation. So we take 11.918, subtract the mean of 11.2, and divide the result by the standard deviation of 0.7. This gives us a z-score of about 1.026. Step 3. Find the probability. We want the probability that z is greater than 1.026. A standard z-table gives us the area to the left. So we do 1 minus the probability that z is less than or equal to 1.026. Looking that up, we get 1 minus 0.8474, which equals 0.1526. The final result? 15.26%. So about 15% of households earn more than $150,000 in this model. Great work getting through that one. Problem 5. Waiting for a call. This ties back to problem 2. A call center receives calls at an average rate of 15 calls per hour, which we know is a Poisson process. So, for part A, which distribution models the time until the next call? The hints are, if arrivals are Poisson, what describes the waiting time? And this distribution has the famous memoryless property. It's the exponential distribution. It's the flip side of the Poisson coin. Poisson counts the number of events in a time period. Exponential measures the waiting time between those events. You can see the formula for the probability that the wait time x is less than or equal to some time t on the screen. Okay, let's finish this. Part B. A call center gets 15 calls per hour. What is the probability that the time until the next call is less than 5 minutes? Let's break it down. Step 1. We need our units to match. The rate lambda is in calls per hour, but our time t is in minutes. So let's convert the rate. 15 calls per 60 minutes gives us a lambda of 0.25 calls per minute. Step 2. Use the formula, which is called the cumulative distribution function, or CDF, with t equals 5 minutes. The probability that x is less than 5 is 1 minus e to the power of negative lambda times t. So that's 1 minus e to the power of negative 0.25 times 5. This becomes 1 minus e to the power of negative 1.25. And when you calculate that, you get 1 minus 0.2865, which is 0.7135. The final answer is 71.35%. There's a pretty high chance the next call will come within 5 minutes. Problem 6. Coin flips. Imagine this. You flip a fair coin 10 times, and you want to count the number of heads. So, for part A, which distribution models this scenario? The key hints are that we're counting successes in a fixed number of trials. If you guess the binomial distribution, you are absolutely correct. We have n equals 10 independent trials, right? And the success probability, p, for a fair coin is 0.5. The formula for getting exactly k heads is right there on the screen. It's c of 10, k times 0.5 to the power of k times 0.5 to the power of 10 minus k, which simplifies nicely to c of 10, k times 0.5 to the power of 10. Okay, so for part B, what is the probability of getting exactly 7 heads? Let's use our formula. We're using the binomial formula with n equals 10, k equals 7, and p equals 0.5. So the probability that our random variable x equals 7 is c of 10, 7 times 0.5 to the power of 7 times 0.5 to the power of 3. Now, 10 choose 7 is 120. We multiply that by 0.0078125 and then by 0.125. And the result is 0.1172, or 11.72%. Not bad at all. Let's move on to problem 7, first sale. A salesperson has a 15% chance of closing a deal on any given call. Part A asks which distribution models the number of calls until their first successful sale. The big clue here is that we are waiting for the first success. First. And here's a little hint. Think geometry. This is the geometric distribution. It's perfect for modeling the number of trials, k, needed for that very first success. The probability of the first success happening on trial k is given by the formula you see here. P of x equals k is 1 minus p to the power of k minus 1 times p. For our salesperson, that's 0.85 to the power of k minus 1 times 0.15. So, for part B, given that a salesperson has a 15% chance of closing a deal, what is the probability that their first sale occurs on their third call? Let's think about what has to happen. This means they have 2 failures followed by 1 success. So, we plug k equals 3 into our formula. P of x equals 3 is 1 minus p to the power of 3 minus 1 times p. That's 0.85 squared times 0.15, which is 0.7225 times 0.15, giving us 10.84%. So there's about an 11% chance their first win is on call number 3. On to problem 8. Dice rolls with categories. You roll a 6-sided die 12 times. And you count how many 1s, how many 2s, and how many other numbers you get. So, part A. Which distribution models this scenario? The hints are we have more than 2 outcomes, but still a fixed number of trials. This is a job for the multinomial distribution. It's basically the big brother of the binomial distribution, handling more than 2 categories. Here our probabilities are P1, the probability of rolling a 1, is 1/6. P2, rolling a 2, is also 1/6. And P3, rolling other, is 4/6. The formula looks a little intense, I know, but it's just counting all the combinations and multiplying by their probabilities. Part B. With those probabilities and a total of n equals 12 rolls, What's the probability of getting 5 ones, 3 twos, and 4 other outcomes? Select. Okay, we need to find the probability that x1 is 5, x2 is 3, and x3 is 4. Let's plug everything into that big formula. We have 12 factorial divided by 5 factorial times 3 factorial times 4 factorial. All of that is then multiplied by 1/6 to the power of 5 times 1/6 to the power of 3 times 4/6 to the power of 4. Okay, that first part, the big fraction, simplifies to 27,720. We multiply that by all those tiny probabilities, and we get approximately 0.00326. Wow. The result is 0.33%. That's a very specific and rare outcome. Problem 9. Multiple sales. A cold caller has a 10% chance of making a sale on any call. Part A. Which distribution models the number of calls needed to achieve 3 sales? Notice the difference here. It's not the first success, but a fixed number of successes. We're waiting for success number 3. This is the negative binomial distribution. It's designed specifically to model the number of trials, k, you need to get a fixed number of successes, r. For our case, with r equals 3 sales and p equals 0.1, you can see the probability formula right on the screen. It's c of k minus 1, r minus 1 times p to the r times 1 minus p to the k minus r. So let's ask a slightly different question for part B. To achieve r equals 3 sales with that success probability of 10%, how many calls would they expect to make? This is actually much simpler than it sounds. The expected value, or the mean, of a negative binomial distribution is just mu equals r divided by p. So for us, that's 3 divided by 0.10, which equals 30. They should expect to make 30 calls to get those 3 sales. It makes perfect sense, doesn't it? Last one. Problem 10. Heights of adults. We know that most adult women are of average height, with fewer being very short or very tall. The data forms a smooth unimodal curve. Part A. Which distribution would be appropriate? The biggest hint is, it's the most famous bell curve. Of course, it's the normal distribution. It models so many natural phenomena where values cluster symmetrically around a mean, which we call mu. Probabilities are found using the standard normal cumulative distribution function, which is that capital phi symbol, after converting our value to a z-score. You can see the formula right there. P of x is less than or equal to x equals phi of x minus mu over sigma. Okay, let's use it. Part B. Male heights are normal with a mean, mu, of 175 centimeters and a standard deviation, sigma, of 6 centimeters. What is the probability a male is between 170 centimeters and 185 centimeters tall? Let's walk through this together, step by step. Step 1. Find the z-score for 170 centimeters. The formula is value minus mean divided by standard deviation. So 170 minus 175 divided by 6. That gives us approximately negative 0.83. Step 2. Find the z-score for 185 centimeters. That's 185 minus 175 divided by 6, which is about 1.67. Step 3. Now we find the probability that z is between negative 0.83 and 1.67. The way we do this is we find the probability that z is less than 1.67 and subtract the probability that z is less than negative 0.83. Looking these up in a z-table, we get 0.9525 minus 0.2033. And the result is 74.92%. And that's it. That's how you solve it. Problem 11. Birthday selection. The problem is simple. A person's birthday can fall on any of the 12 months of the year. So for part A, which distribution models the month in which someone is born? The key question to ask yourself is on the slide. Are all 12 months equally likely? If we assume that births are spread out evenly, then yes, each month has the exact same chance. This means we're dealing with a discrete, uniform distribution. For a random variable x, which represents the month number, the probability of being born in any specific month k is simply 1 divided by 12. Easy as that. Okay, let's build on that. For part B, what is the probability that someone is born in the first quarter? That would be January, February, or March. Well, since each month has a 1 in 12 probability, and the first quarter includes 3 months, we just add them up. The probability of the first quarter is the probability of January plus the probability of February plus the probability of March. That's 1/12 plus 1/12 plus 1/12, which equals 3/12. And that simplifies down to a result of 1/4, or 25%. Okay, on to problem 12, a marketing campaign. An email campaign is sent to 20 subscribers. The open rate is consistently 25%. So, part A. Which distribution models the number of subscribers who open the newsletter? Take a look at the hint on the slide. We are counting successes in a fixed number of trials. That's right, it's the binomial distribution. It's perfect for this scenario. We have n equals 20 trials, which are our subscribers, and each trial has a success probability, p, of 0.25, which is the chance they open the email. You can see the formula on the screen for the probability of exactly k people opening. It's c of 20, k times 0.25 to the k times 0.75 to the 20 minus k. So, for part B, let's use that formula. What is the probability that exactly 5 subscribers will open the newsletter? Let's walk through this. We have our binomial distribution with n equals 20 and p equals 0.25. We need to calculate p of x equals 5. Looking at the formula, that means we calculate c of 20, 5, which comes out to 15,504. Then we multiply that by 0.25 to the power of 5, and then by 0.75 to the power of 15. It's a bit of a calculation, but when the dust settles, the result is approximately 0.2023. That's a 20.23% chance. Next up, problem 13, machine lifetime. An electronic component's failure probability is constant, no matter its age. Part A. Which distribution models the component's lifetime? The critical hint is right there. The component has no memory of how long it's been running. That key feature points directly to the exponential distribution. It's used to model the time until an event occurs in a process where the event rate is constant. The probability that the component lasts longer than some time t is given by the formula e to the power of negative lambda t, where lambda is the failure rate. Now for part B. The component follows an exponential distribution with an average lifetime of 10,000 hours. What's the probability it will last longer than 12,000 hours? Let's break this down into 2 simple steps. Step 1. We need to find the failure rate, lambda. For an exponential distribution, the mean is just 1 divided by lambda. So, lambda equals 1 divided by 10,000, which is 0.0001 failures per hour. Okay, now for step 2. We calculate the probability that x is greater than 12,000. We just plug our numbers into the formula. It's e to the power of negative 0.0001 times 12,000. That simplifies to e to the power of negative 1.2, which is approximately 0.3012. So the result is a 30.12% chance. Problem 14. Stock prices. A stock price can't be negative, and its future value is often right-skewed because of compounding gains. Part A. What distribution is commonly used to model stock prices? The hint is a big one. If the logarithm of your data looks normal, then you're dealing with a log-normal distribution. It's a really important one in finance. A random variable x is log-normally distributed if its natural logarithm, ln of x, is normally distributed. So, if x is our stock price, then the natural log of x follows a normal distribution. Okay, let's apply this. Part B. The log of a future stock price is normal with a mean of 3.8 and a standard deviation of 0.2. What's the probability the actual stock price will be less than $40? We are going to walk through this entire process together, step by step. First, step 1. We have to transform our price threshold of $40 to the log scale. The natural log of 40 is approximately 3.689. Step 2. Now we calculate the z-score for that log value. The formula is value minus mean divided by standard deviation. So 3.689 minus 3.8, all divided by 0.2. This gives us a z-score of about negative 0.555. Finally, step 3. We just need to find the probability that z is less than negative 0.555 from a standard z-table. And the result is 28.9%. Problem 15. The free throw. A basketball player attempts one free throw shot. Part A. Which distribution models whether the shot goes in? The hints are key. Just one trial, 2 outcomes. This is the simplest one of all. It's the Bernoulli distribution. It's for a single experiment with only 2 possible outcomes, success or failure. We say x equals 1 if they make the shot with probability p, and x equals 0 if they miss with probability 1 minus p. Part B. This player makes 75% of their free throws, so p equals 0.75. The question is, what's the probability they make this shot? And what's the expected value? This is almost a trick question because it's so straightforward. The probability of success is simply p itself. So the probability they make the shot is 0.75. And here's the cool part. The expected value of a Bernoulli trial is also p. So the expected value is also 0.75. It's that simple. Great job on this set. Problem 16. Finding a defect. An inspector checks items from an assembly line where 2% of items are defective. First question. Which distribution models the number of items checked until finding the first defective item? The key here is that we're counting trials until the first success. That, my friends, is the geometric distribution. This models the number of trials, k, needed for the very first success. In our case, a success is finding a defect, so p is 0.02. The probability of that first defect showing up on the kth item is p of x equals k equals 1 minus p to the power of k minus 1 times p, which for us is 0.98 to the k minus 1 times 0.02. So, part B. The probability of a defect is 0.02. How many items on average would the inspector expect to check before finding that first defective one? Here's the great thing about the geometric distribution. The expected value, or the mean, is just 1 divided by p. It's super intuitive. So mu equals 1 divided by 0.02, which is exactly 50. The inspector expects to check 50 items. Let's move on to problem 17, website page views. A news article gets 50 page views per minute on average. Part A. Which distribution models the number of page views in a 6-second window? We're counting events in a fixed interval. That's the telltale sign of a Poisson distribution. But first, we have a little prep work to do. We need to scale the rate, lambda, for our 6-second window. A 6-second window is 1/10 of a minute. So we take 50 views per minute and multiply by 1 minute per 10 windows, giving us a lambda of 5 views per 6 seconds. Now we can use the formula. The probability of k views is lambda to the k times e to the negative lambda, all divided by k factorial. Okay, part B. The rate, lambda, is 5 page views per 6-second window. What's the probability that it receives no page views in a specific 6-second window? We need to calculate p of x equals 0 using our lambda of 5. So it's 5 to the power of 0 times e to the negative 5, all divided by 0 factorial. And remember, anything to the power of 0 is 1, and 0 factorial is also 1. So it just simplifies down to e to the negative 5, which is approximately 0.0067. That's a tiny probability, just 0.67%. Problem 18. The random number generator. A computer's random number generator produces real numbers between 0 and 1. So, for part A, which distribution models these generated numbers? Let me ask you this. Is any number more likely than another? Nope. Every number between 0 and 1 has an equal chance of being selected. This is a uniform distribution, the continuous version. The probability that our number x falls between some value a and b is just b minus a for any valid interval between 0 and 1. It's beautifully simple. Which brings us to part B. Numbers are generated uniformly between 0 and 1. What's the probability a generated number falls between 0.3 and 0.7? Just like the formula said, the probability is simply the width of the interval. So p of x being between 0.3 and 0.7 is just 0.7 minus 0.3. The result is 0.4, or 40%. Problem 19. Basketball shots. A player makes 70% of her free throws. We're interested in the number of attempts to score her 5th basket. Part A. Which distribution models this? Notice we're not waiting for the first success anymore. We're waiting for the rth success. This is a job for the negative binomial distribution. It's the perfect tool for modeling the number of trials, k, to get a fixed number of successes, r. For r equals 5 baskets and a probability of p equals 0.7, the formula looks a little intense, but it's not so bad. P of x equals k is k minus 1 choose r minus 1 times p to the r times 1 minus p to the k minus r. Let's use it. Part B. We need the fifth basket, so R equals 5 with a success probability of 0.7. What's the probability that she scores her fifth basket on her seventh attempt? We are going to walk through this calculation step by step. We need to calculate P of X equals 7, so we plug in our numbers. That's 7 minus 1, choose 5 minus 1, times 0.7 to the fifth power, times 0.3 to the power of 7 minus 1. 5. Let's simplify that. It becomes 6 choose 4 times 0.7 to the fifth times 0.3 squared. 6 choose 4 is 15. 0.7 to the fifth is about 0.168, and 0.3 squared is 0.09. Multiply those all together, and you get approximately 0.2269. The result? 22.69%. Problem 20. Customer preferences. A restaurant observes customer orders, 60% coffee, 30% tea, and 10% juice. We select 10 customers. Part A. Which distribution models the number ordering each beverage? It feels like binomial, but with more than 2 categories. And that's exactly what it is. It's the multinomial distribution. It generalizes the binomial for n trials with c possible outcomes. In our case, n is 10 customers, and our probabilities are P1 equals 0.6, P2 equals 0.3, and P3 equals 0.1. The formula is a big one. It's n factorial divided by the product of all the k factorials times each probability raised to its corresponding k. So, for our last question, Part B, the probabilities are 0.6 for coffee, 0.3 for tea, and 0.1 for juice, with 10 total customers. What is the probability that exactly 6 ordered coffee, 3 ordered tea, and 1 ordered juice? Let's plug everything into our big formula. We need P of X coffee equals 6, X tea equals 3, and X juice equals 1. That's 10 factorial divided by 6 factorial times 3 factorial times 1 factorial. Then we multiply that by 0.6 to the sixth times 0.3 to the third times 0.1 to the first. Okay, the fraction part simplifies to 840. The probabilities become about 0.046, then 0.027, and 0.1. Multiply it all out, and we get approximately 0.1058. Our final answer, 10.58%. Number 21. Daily temperature. The daily high temperature in a city varies around an average, with most days near that average and fewer extremely hot or cool days. So, for Part A, what distribution describes these daily temperatures? Well, let's look at the clues. The data clusters around the average, and it's symmetric. This is a classic. It's the normal distribution. This is the famous bell curve we use for continuous data that's clustered around a mean, which we call mu. Probabilities are found using the standard normal CDF, denoted by that capital Greek letter phi. The formula is P of X is less than or equal to X equals phi of the quantity X minus mu, all divided by sigma. Okay, let's use it. Part B. Summer temperatures are normal with a mean of 78 degrees Fahrenheit and a standard deviation of 5 degrees. The question is, what percentage of days have temperatures below 70 degrees Fahrenheit? We are going to walk through this calculation step by step. First, we need to calculate the z-score for 70 degrees. The formula for the z-score is z equals x minus mu divided by sigma. For us, that's 70 minus 78, which is negative 8, divided by 5. This gives us a z-score of negative 1.6. Now we just have to find the probability that z is less than negative 1.6 by using a z-table. And the result is 0.0548, or 5.48%. Next up, problem 22, quality control. A production line produces 4% defective items. We take a random sample of 10 items. Part A, which distribution models the number of defective items? Let's see, we have a fixed number of trials and only 2 outcomes, defective or not. That's right, it's the binomial distribution. We have n equals 10 independent trials with a success probability p of 0.04. The probability of getting exactly k defective items is given by the formula p of x equals k equals c of 10 comma k times 0.04 to the kth power times 0.96 to the power of 10 minus k. Okay, on to part B. We have a binomial distribution with n equals 10 and p equals 0.04. What is the probability that none of them are defective? Let's solve this. We need to calculate p of x equals 0. This means all 10 items have to be good, and the probability of an item being good is 96%. So, using our formula, p of x equals 0 is c of 10, 0 times 0.04 to the power of 0 times 0.96 to the power of 10. Now, c of 10, 0 is just 1, and 0.04 to the 0 is also 1. So it simplifies to just 0.96 to the 10th power, which is approximately 0.6648. The result, 66.48%. Problem 23. Playing card. A single card is drawn from a well-shuffled standard deck of 52 cards. Part A. Which distribution models the suit, hearts, diamonds, clubs, spades, of the drawn card? Here's a hint. Is any suit more likely than another? Of course not. That's why it's a uniform distribution, the discrete version. Since there are 13 cards of each of the 4 suits, all outcomes are equally likely. The probability of x equaling any given suit is 13 divided by 52, which simplifies to 1/4. That's true for each of the 4 suits. So, for part B, the probability of drawing any specific suit is 1/4. What is the probability the drawn card is either a heart or a diamond? This is a nice, simple one. We want 2 specific suits out of 4 total suits. All we have to do is add their probabilities together. The probability of heart or diamond is the probability of a heart plus the probability of a diamond. That's just 1/4 plus 1/4, which gives us 2/4, or 50%. Easy as that. Let's roll into problem 24, rolling a specific number. You are rolling a standard 6-sided die repeatedly until you get a 4. Part A. Which distribution models the number of rolls until the first 4? Notice we're not counting total successes here. We're waiting for the first one. This is the geometric distribution. It models the number of trials, k, required to get the very first success. For a success probability p of 1/6, the probability of the first 4 happening on roll k is p of x equals k equals the quantity 1 minus p to the power of k minus 1 times p. For us, that's 5/6 to the k minus 1 times 1/6. Let's apply this. For part B, the probability of rolling a 4 is p equals 1/6. What is the probability that the first time you roll a 4 is on your 5th roll? Okay, let's think this through. This requires 4 failures, that is, not a 4, followed by 1 success, which is a 4. We just plug k equals 5 into our formula. P of x equals 5 is the quantity 1 minus 1/6 to the power of 5 minus 1 times 1/6. That simplifies to 5/6 to the 4th power times 1/6. 5/6 to the 4th is about 0.4822, and we multiply that by 0.1667, giving us approximately 0.0804. The result, 8.04%. Problem 25. Email arrivals. Emails arrive in your inbox at an average rate of 10 per hour. Part A. Which distribution models the time between 2 consecutive emails? If the arrivals are a Poisson process, what describes the waiting time? Hint. It's the memoryless one. You got it. It's the exponential distribution. This models the time between events in a Poisson process. The probability that the wait time, x, is less than or equal to some time t is given by the formula 1 minus e to the power of negative lambda t, where lambda is the event rate. So for our final question, part B, emails arrive at an average rate of 10 per hour. What is the probability that the time between 2 consecutive emails is between 3 minutes and 9 minutes? Let's break it down. Step 1. We have to convert our rate, lambda, to emails per minute. The rate is 10 emails per 60 minutes, so lambda is 1/6 of an email per minute. Super important step. Step 2. We need to calculate p of 3 is less than x is less than 9. We do this by finding p of x is less than 9 and subtracting p of x is less than 3. Using our formula, that's the quantity 1 minus e to the negative 1/6 times 9 minus the quantity 1 minus e to the negative 1/6 times 3. Let's simplify those exponents. That becomes 1 minus e to the negative 1.5 minus 1 minus e to the negative 0.5. When you distribute that negative sign, the ones cancel out, and we're left with e to the negative 0.5 minus e to the negative 1.5. Plugging in the values, that's about 0.6065 minus 0.2231, which equals 0.3834. Our final result, 38.34%. Number 26. It's a classic, the coin flip. You flip a fair coin once. Part A. What distribution describes the outcome of getting heads? Think about it. We have one flip and only 2 possible outcomes. That's right, it's the Bernoulli distribution. This is the perfect distribution for a single trial with 2 outcomes, like success or failure. In this case, x equals 1 for heads with a probability p of 0.5, and x equals 0 for tails with a probability of 1 minus p, which is also 0.5. Simple enough, right? So, for part B, the outcome of a fair coin flip is a Bernoulli trial with p equals 0.5. What is the probability of getting heads? And what is the variance? Well, the probability of heads is simply p, so that's an easy 50%. Now for the variance. The variance for a Bernoulli distribution is p times the quantity 1 minus p. So we just plug in our numbers, 0.5 times 1 minus 0.5, which equals 0.25. Easy peasy. Moving on to problem 27. Biological growth. The size of organisms often exhibits a right-skewed distribution. Why? because growth is proportional to current size. So, Part A. What distribution would you use to model such sizes? Here's a hint. When growth is multiplicative, taking the logarithm makes it normal. It's the log-normal distribution. A variable x is log-normally distributed if its natural logarithm, ln to eke, is normally distributed. So if x is our organism size, then the natural log of x follows a normal distribution with a mean of mu sub log and a variance of sigma sub log squared. Okay, let's apply this. For Part B, the log of a bacterium size, that's ln of size, is normal, with a mean of 2.5 and a standard deviation of 0.3. The question is, what is the probability that a bacterium is larger than 15 micrometers? First, step 1. We have to transform our size threshold to the log scale. So we take the natural log of 15, which is approximately 2.708. Next, step 2. Calculate the z-score. Remember the formula? It's our value minus the mean divided by the standard deviation. So we get z equals 2.708 minus 2.5, all divided by 0.3. That works out to approximately 0.693. And finally, step 3. We need to find the probability that z is greater than 0.693 from a z-table. This is the same as 1 minus the probability that z is less than or equal to 0.693. Looking that up, we get 1 minus 0.7557, giving us our final result, 24.43%. Problem 28. Typo count. A proofreader finds an average of 2 typos per page in a manuscript. Part A. Which distribution models the number of typos on a randomly chosen page? We're counting discrete events with a known average rate. Sound familiar? It's the Poisson distribution. This distribution is perfect for modeling the number of events occurring in a fixed interval of time or space given a constant mean rate, which we call lambda. For lambda equals 2 typos per page, the probability of finding k typos is given by the formula you see here, lambda to the k times e to the negative lambda, all divided by k factorial. So for Part B, the rate of typos is lambda equals 2 per page. What is the probability that a randomly chosen page has exactly 1 typo? Let's use our formula. We need to calculate p of x equals 1 using lambda equals 2. So we plug in the numbers. P of x equals 1 is 2 to the power of 1 times e to the negative 2, all divided by 1 factorial. That simplifies to just 2 times e to the negative 2. Since e to the negative 2 is about 0.1353, we get 2 times that, which is approximately 0.2707. The result, 27.07%. Okay, problem 29, medical trial. An experimental drug cures 60% of patients. If 7 patients are treated, Part A, which distribution models the number of patients cured? We have a fixed number of patients and 2 outcomes for each, cured or not cured. You know this one. It's the binomial distribution. We have n equals 7 independent trials, where each has a success probability of p equals 0.6. The probability of exactly k patients being cured is given by the big formula here. C of 7k times 0.6 to the power of k times 0.4 to the power of 7 minus k. Now for the application, Part B. We have a binomial distribution with n equals 7 and p equals 0.6. What is the probability that at least 6 are cured? At least 6 means we need to find the probability of exactly 6 being cured and the probability of exactly 7 being cured, and then add them together. So we need to calculate p of x is greater than or equal to 6, which equals p of x equals 6 plus p of x equals 7. Let's do p of x equals 6 first. That's c of 7, 6, times 0.6 to the 6th, times 0.4 to the 1st. That gives us approximately 0.1306. Now for p of x equals 7. That's c of 7, 7, times 0.6 to the 7th, times 0.4 to the 0th power. And that comes out to about 0.0279. Now we just add them up. 0.1306 plus 0.0279 gives us our result, 15.85%. And our final problem, number 30, lottery drawing. In a lottery, balls numbered 1 to 50 are placed in a machine, and one ball is randomly selected. Part A. Which distribution models the number on the selected ball? Here's the key question. Does any ball have a better chance of being selected? Of course not. This is the uniform, specifically the discrete uniform distribution. All 50 outcomes from ball number 1 to 50 are equally likely. The probability of selecting any specific ball, k, is simply 1 divided by 50. That leads us to our last question, Part B. There are 50 equally likely outcomes. What's the probability the selected ball has a number between 20 and 30 inclusive? Okay, let's think this through. The numbers we want are 20, 21, 22, all the way up to 30. How many numbers is that? Be careful here, it's not just 30 minus 20. It's 30 minus 20 plus 1, which gives us 11 favorable outcomes. The probability is just the ratio of those favorable outcomes to the total number of outcomes. So that's 11 divided by 50. And our result is 22%.